In this graph, we once again go back to the Cayman Island example that we first used in graph 7.3 to introduce a pure substitution effect. Now, however, we're going to add some numbers. We'll assume that the budget with which my brother and I arrive in the Cayman Islands is $2,000. The price of taking a cab or a taxi is $1 per mile. The per mile cost of riding around in a rental car is 20 cents per mile, or just 1/5 of the price of riding in a taxi. We'll begin by assuming that our tastes are Cobb-Douglas, with an exponent of 0.1 on the miles driven good and 0.9 on the all other goods, and then we'll increase the elasticity of substitution to see how the graph changes. The blue taxi budget constraint therefore has a vertical intercept of 2,000 and a slope of -1, which is equal to the per mile cost of driving around in a taxi. The per mile cost of driving around in a rental car, on the other hand, is only 20 cents per mile, so the slope of the magenta rental car budget is only -0.2, but its intercept is lower because we have to pay a fixed rental car fee before we ever start driving the first mile in the rental car. In the text, we calculated that fixed rental car fee for our scenario to be equal to $298 per week. We'll get back to how we calculated that in a moment. For now, we have two budget constraints, the blue taxi budget constraint and the magenta rental car budget constraint. We then draw in two indifference curves that derive directly from the utility function we're using, the Cobb-Douglas utility function, with exponents of 0.1 and 0.9. The green indifference curve is tangent to both the blue and the magenta budget constraints. Note that whenever we're using Cobb-Douglas utility functions, we're implicitly assuming an elasticity of substitution equal to 1. We learned how to calculate the optimal bundle A on the blue budget constraint back in Chapter 6. What we do is we maximize utility, subject to the blue budget constraint, to find that this optimal bundle has $1,800 in other goods consumption and 200 miles driven on the island. At the optimal bundle C on the magenta budget constraint, we're driving more miles, 851 versus 200, and consuming less in other goods, $1,532 versus $1,800. In the text, we didn't know what the rental car fee was, so we couldn't use the usual utility maximization problem to solve for bundle C. In other words, we couldn't simply say, let's have the consumer maximize utility subject to the magenta budget constraint, because we didn't know exactly where the magenta budget constraint was. We just knew its slope. What we did instead was, we said we know that this consumer operates on the green indifference curve, because my brother and I are indifferent between driving a rental car and taking taxis, and therefore we'll take the green indifference curve as fixed and ask the question, what's the minimum expenditure necessary in order to reach that indifference curve when the per mile cost of driving is only 20 cents? In other words, we did the expenditure minimization problem. Once we derived bundle C, the expenditure minimizing bundle, given that we reached the green indifference curve, we could then multiply that bundle by the relevant prices to find out that it would cost us $1,702 to get to that indifference curve when the price for a mile driven is 20 cents per mile. Thus we could conclude that the rental car fee must have been the difference between the initial $2,000 and the $1,702 that we need to spend in order to reach the green indifference curve with the rental car per mile cost. The first order conditions of our utility maximization and expenditure minimization problems tell us that the marginal rates of substitution will be equal to the slopes of the budget constraints at the optimal bundles. This is true in our case because there are no corner solutions when tastes are Cobb-Douglas, because Cobb-Douglas tastes give rise to maps of indifference curves that do not intersect the axes. They can also be represented as a special case of constant elasticity of substitution utility functions, where rho is set equal to 0, giving us an elasticity of substitution equal to 1. In panel B, we'll construct a similar graph, and the only thing we'll change is that we are going to assume that my brother and I now have a constant elasticity of substitution utility function where the elasticity of substitution is equal to 2 rather than to 1, which it had been in panel A. We are also adjusting the other parameter in the utility function to make sure that the original bundle A on the taxi budget constraint remains the same as it was in panel A, so that we can easily compare the two scenarios. The indifference curves drawn here are then derived directly from the constant elasticity of substitution utility function with elasticity of substitution equal to 2, and the magenta budget constraint is drawn so as to be tangent to the same green indifference curve that's tangent to the blue budget constraint at bundle A. We now label the point of tangency with the magenta budget constraint as B, and we notice that B lies much further to the right than C did in panel A. Now, we're driving 2,551 miles on the island when we rent the car, as opposed to the 851 miles we drove in panel A. And we're consuming only $918 of other goods, as opposed to the $1,532 in other goods we consumed in panel A along the magenta budget constraint. We again didn't know exactly where the magenta budget constraint lies in this case. All we know is that it has a slope of minus 0.2. What we do know is that it's tangent to the green indifference curve, the same indifference curve that's tangent to the blue taxi budget constraint. So what we do instead of utility maximization, we ask, what's the minimum expenditure necessary to get to the green indifference curve when the price per mile driven is just 20 cents? Thus we set up the expenditure minimization problem, and we derive the expenditure minimizing bundle B. We then multiply 2,551 by 0.2 and add it to 918 to come up with the fact that it takes $1,428 to get to bundle B when the price of per mile driven is only 20 cents. Thus, it must be that the rental car fee is the difference between $2,000 and $1,428, which in our case is now $572. The mathematical problem used to solve for bundle A is therefore the utility maximization problem that's written here as equation 7.18, and the mathematical problem used to solve for bundle B is the expenditure minimization problem written here as equation 7.19. The utility level, or the label, of the green indifference curve is 1,250, which we derived by simply taking the bundle A and plugging it into the utility function to find how much utility the consumer actually gets at bundle A. We had already shown in graph 7.4 that the greater degree of substitutability that's built into indifference curves, the greater will be the substitution effect. What we show here is that we can say the same thing mathematically by saying that the greater the elasticity of substitution built into the utility function, the greater will be the accompanying substitution effect. We start in panel A with an elasticity of substitution equal to 1 and go in panel B to an elasticity of substitution equal to 2. In panel A, the substitution effect is the move from bundle A to C, and in panel B it's the move from bundle A to B. Clearly the move from A to B is much bigger than the move from A to C, so the substitution effect has gotten bigger as we increase the elasticity of substitution.